There we go. I have to say, got it. Perfect. Okay, so let's start with a little bit of background on RBR. We have been around for quite a while, since 1973. So about 48 years developing really high precision, low power oceanographic instrumentation to WOSI standards. We're headquartered in Canada. We have a lot of ocean, a lot of coastline here with a variety of different ecosystems. So it's very, very exciting being here. We have offices in Ottawa, which is where the headquarters are, as well as Halifax, where I'm based. We have offices in the US, we have offices in China, in Australia, and in France. And we have over 80 dedicated, relatively technical staff members. And they're all really nice people. If you have talked to anyone at RBR through sales or support, you find that we're a pretty nice bunch to talk with. And we also have a really good network of technical sales and support throughout the world through our agent channel as well. So you can basically find us anywhere in any country in the world. And on that note, depending on where you're coming from, you probably have seen some of our instrumentation in one way or another, whether it's you know, in the really warm coastlines all the way to the Arctic or the Antarctic. Our instruments really have been deployed in all continents and in all oceans. So that's just a little bit of background. And what do we do? So our focus really can be categorized into these 4 high-level areas. Sensors, which are really the core of what we're going to be talking about today. This is really what measures the parameters of the ocean and then delivers it to whether it's a logger or up to the cloud or something like that, or to a smart mooring. Then we have the loggers, which are really a sensor hub. It puts together the electronics to put all the sensors into one channel or one data stream that can be either autonomously recorded within the logger or real-time streamed out. It has batteries and it can really do missions for years autonomously at a time. We also have the OEM series of products, which is taking some of the sensors we have and refactoring them in form factors that fit or integrate into specific platforms. And that's mostly in the float and glider and AUV communities that we go into the OEM sides. So we have many integrations into that. I'll show a couple of those. And then we have what we call systems, which is many of the elements that are outside, around the sensors and the loggers to either extend the mission, extend the deployment, or send the data up, stream it out to your desktops. So let me focus now on the sensors, which is what we call the RBR Coda series. So the Coda sensors can measure different parameters such as temperature, depth, PAR, which is light, optical dissolved oxygen. And these are all under the umbrella of the Coda. And these are really the main sensors that we develop. These are just some of them. We have a variety of other sensors. These are the key ones. And these are the key ones that we really work with Sofar to integrate into the smart mooring. Now, one key thing about the Coda series is that there's no power or no logging. Really, they're smart sensors. They can be configured to burst mode, to wave, to tide, that kind of thing. But they really need to be powered. So they need that power coming in from the smart mooring, and then they stream the data out into the telemetry that the spotter buoy will be using. Again, this is using RS-232 communication. It doesn't really matter so much to the end user because it's all integrated into the system. I'll go into some details on the specific ones. The workhorse of our Coda series is a Coda T. We have deployed thousands and thousands of Coda Ts throughout the world. These are extremely reliable temperature sensors, so range between -5 to 35 degrees Celsius. They have accuracies in the order of degrees Celsius, plus minus milli-degrees Celsius, resolution of 0.00005 degrees Celsius. We have two versions of this, which is the standard and then a fast one, fast thermistor. The standard is a 1 second time constant, and the fast one is 100 milliseconds time constant, so 0.1 second. And these can be, again, available in different sampling rates from 2 Hertz all the way to 32 Hertz. Again, if you have questions, anything like that comes to mind you want to ask, just put it in the chat and we'll address it at the end. Then we have the brother to the Coda T is a Coda D. This is a pressure sensor, ranges all the way from 20 meters. It could be less. The calibration is starts at really 20 meters all the way to 1,000 meters, or sorry, 1,000 dbar, about equivalent to 1 dbar to 1 meter. Has an initial accuracy of 0.05% of full scale, and that should be resolution, not time constant. It's resolution of 0.001% full scale. Again, this one has multiple sampling rates available from the standard 2 Hertz all the way to 32 Hertz. And then you can also find them in tide and wave modes that allow for tide and wave and sea level analysis as well in post-processing. Then we have bringing them both together is a Coda TD. Same parameters, it's just in one single data channel or one single data stream with 2 channels in it. And I won't go through the specific details because it's the same as the T and the D. It's just in one integrated small sensor. The other kind of the newer in the last few years, but now broadly used Coda sensor is a TODO, which stands for temperature and optical dissolved oxygen. Has a range of 0 to 500 micromoles, which is equivalent in range to a saturation from 0 to 120%. Initial accuracy, plus minus 8 micromoles or plus minus 5%, whichever is the highest of the two, and a resolution of less than 1 micromole. Again, this can be configured to sample anywhere from 1 Hertz, so 1 sample per second, all the way to once every 24 hours. And this specific Coda goes down to 6,000 meters. And this is the one body it has. It's a titanium body. It does have 3 time constant versions. There is a fast, which is a 1 second time constant. So this especially useful when you're doing profiling. We use it a lot in gliders or in the Wirewalker, in those kind of profiling platforms. The standard, which is the 8-second time constant, and a slow one, which is for moored application, is a 30-second time constant, and that one can be wiped, meaning you can attach a wiper to it. And these are very similar, especially the slow and the standard, to the Andara optodes. If you're familiar with those, same specs basically, but then we also have the fast, which is kind of unique to us. And then the last Coda I wanted to talk about is the Coda PAR. This is again to measure light, or more specifically photosynthetically active radiation. So the type of light in the photic zone around the top 200 meters of the water column. And this one specifically has a range between 400 nanometers or 700 nanometers, or more clearly just a visible range, visible light. An accuracy of plus minus 2%. Somehow the wavelength is repeated there, apologies. And it can sample up to 16 Hertz. Again, this one has, if you're really measuring around the photic zone, a maximum depth of 560 is plenty for that. So that really covers the Coda series that we have. Very quickly now, I wanted to go up to the loggers that we have and the systems that we have. So you have an idea of the entire picture of what RBR is. And then I'll pass it on to the Sofar folks for them to talk about the spotter buoy and the smart mooring. So our compact loggers, what is a logger? It's really a recorder. It's a data recorder. It integrates the same sensors that I was talking about before into a very small compact unit that is self-contained, autonomous. They only require one AA battery of any chemistry. So that makes it very easy when you're doing deployments or doing recovery and have to replace batteries and you're out in the middle of nowhere. You can really go out to a grocery store, convenience store, and get a battery there to at least continue the mission if necessary. They come in 1 or 2 channels, and the way you download the data is you open them up, and it has a little USB-C port inside. And these come in either single channel or dual channel. The single channel ones are called the RBR solos, and we have temperature, depth, oxygen, turbidity, and power as well. Kind of the same as what we had in the other one in the Codas. And the dual channels are temperature and depth, or TDs, and temperature and optical dissolved oxygen. So very much taking what you had in the Coda, but now making it into a little logger as well. And the standard versions have a depth rating up to 1,700 meters, and the titanium ones up to, and in some cases, a little bit over 10,000 meters. We have had some that have gotten to the bottom of the Challenger Deep, which is, I think it was measured to be about 10,900. Taking it all kind of a step further is the standard loggers. And these are now larger type of data recorders. These are really our sensor hubs. They have 8 AA batteries inside, all the way up to 10 possible channels, or 10 possible different parameters you can be measuring. They have twist activation on the battery end cap, where it vibrates to let you know that it's on before you deploy it. They have Wi-Fi available so that you can actually pick up the data without having to open up the unit, even when it's still just at the surface. And again, we can process the data, and you can connect with Ruskin, specifically Ruskin Mobile, connecting through Wi-Fi. In this series, and some of these are some that we're investigating to integrate with Sofar as well, are, the most popular one would be the CTD, conductivity, temperature, and depth. But looking at them throughout, we have the Virtuoso, which is a 1 sensor, the Duo, which is the 2 sensors. Brevio is a very tight little one with a little connector in the back. They all can have a serial connection at the back, but this one is only CTD. Concerto, all the way to 5 different sensors, fairly compact form factor. And then the Maestro, which is has a big head with many sensors, all the way to 10. And there's a list of different possible parameters that we can have in that, including CO2, methane, voltage if you have your own sensor. So they're very versatile loggers. And we're looking at some of them, specifically CTD, potentially to integrate with the smart mooring. And as we're coming up with an anti-fouling technology that should be coming up a little bit later this year in our CTD, then it may be interesting to keep an eye open for an integration of that one with Sofar as well. Quickly, I wanted to talk about our Quartz series. Quartz is a specialized type of pressure gauge. This is using the DigiQuartz, the Pearl Scientific DigiQuartz pressure gauge. Very high resolution and very high stability, all the way from, pretty much at the surface for wave, tide, and sea level measurement down to 7,000 meters for seismic and geodesy measurements as well. And we have a number of these. The 2 white ones at the top are surface ones, the Quartz Q and Q+, and then our BPRs at the bottom, bottom pressure recorders and the bottom pressure recorder 0, the BPR 0, which is using the A0A correction to really eliminate the drift, virtually all the drift. So it's meant for very long deployments. And then we have the APT, which is a BPR, but it also includes a triaxial quartz accelerometer. So very useful for seismic studies and has been deployed now in a few tsunami detection systems throughout the world. Very quickly on the OEM side, this is, as I said before, refactoring some of the sensors that we have to really fit into these float and glider / AUV applications. So the key here is low power electronics. They're a sensor hub, and they really integrate into the form factor of those units. So the ones that we have had around the longest are the RBR Argo series. If you're familiar with the Argo program, the international Argo program, we're part of that at this stage in the pilot stage, and we have this integrated into Teledyne, MRV, NKE, MetOcean, NOTC, Argo floats. And it's the same CTD that we have in the Concerto or in the Brevio that you saw before, but in a form factor that fits these floats quite well. And again, the key for Argo is to be able to extend the missions and really reduce that cost per profile. So we are able to do that so that we can get the most data up into the Argo system. The next one is Delegato. And Delegato is a streamlined CTD specifically designed for gliders and AUVs, where low hydrodynamic drag is key, so that you reduce any kind of energy use or energy wasted in drag, such that you can have long missions. Again, low power increases sample density. And the interesting thing is, if you know some of the other CTDs available around the world that sometimes require pumps in order to operate, to get your conductivity and then salinity, we don't require a pump. That means that it's completely quiet, and it has been used very well with passive acoustic sensors when they want to do any type of really careful listening, if you want, and as well as turbulence studies. So that's really the core of our OEM series, is the Argo and the Delegato. And then finally, the systems that we put together to kind of bring, one before, is really what enables all these loggers and sensors to really get through the deployment mission and then get that data up to our end users' desktops. So we have integrations with platforms such as the Sofar Smart Mooring for moored systems, of course, and the Wire Walker for profiling applications. We have, of course, our software that puts it all together, and Ruskin, both for desktop and mobile, allows you to simulate, to configure, to deploy all of our instruments in one single piece of software. And then we have other additions to any system, which is by external power canisters such as a Fermata, or brains and memory such as a Servata, and telemetry and hosting with a Cervelo, and as well as inductive modems such as our mooring line modem 1000. So that gives you an overall picture of everything we do at RBR and our history and how established we are. And then with that, I really wanted to thank you for taking the time to listen to that. And now let's take it over to the Sofar team so that they can tell you how this is integrated into their spotter buoy and smart mooring and the value to you. So thank you. So I think I pass it on to Sebastian.
Hi everyone. Can you see my screen?
We can.
Yeah, all right, first try.
Yeah.
Amazing. Hi, everyone. My name is Sebastian Boule. I'm originally French, you can probably hear. I'm an oceanographer at Sofar and Director of Business Development. I'm based in New Zealand, but our office is actually located in San Francisco. And so for those of you that don't know us yet, we're a team of about 45 oceanographers and engineers, and we build devices and software to better understand our oceans. So what you see here is our mission statement. We want to connect the world's oceans, and fundamentally, we're doing this to help progress our understanding of the marine environment. But unfortunately, this approach is not so simple and presents some complexities. And the big bottleneck, as most of you would know, is the access to in situ data to marine observations. And this is typically made complicated by the cost of the sensors, the complexity of the deployment itself, or the accessibility of the data. How do you actually get the data out of the sensor? And our vision really is to empower everyone, and not just scientists and engineers, to collect the marine data that matters to them. Practically, that means offering affordable, convenient, and flexible sensors. And this is where our initial ID comes in. Believe it or not, it all starts with a simple ID to make it easier to gather data. And so we started about 2016. The spotter buoy that you see here was developed for a research project. And with the evolution of hardware and sensor technology, the availability of global satellite communication networks, we're now living in an era where it's possible to build tens of thousands of remote monitoring and sensing devices that report back the data to a centralized repository, all in real time. It's the IoT approach that I'm sure you've heard about. This here is our spotter buoy that some of you may already be familiar with. I recognize a lot of names in the attendees list here. We designed the buoy to be a weather buoy that's about 30 times more cost-effective, all included, than the existing weather buoys. It can be used as an anchored system for coastal monitoring, as a standard wave buoy, but also as a drifter. So the exact same device can be used for multiple kinds of purposes. The small size means that we can bring the weight down. So you don't need a large vessel anymore. We've had people deploy the buoys using kayaks, using standard paddleboards, and all kinds of crazy ideas. And so the instrument can be really hand deployed, and you can use small vessels of opportunity, and it become accessible to citizen scientists. And this small size and ease of deployment is especially important at the moment when, with the travel restrictions due to COVID, and being able to task local people to deploy the marine sensors at your research locations without having to get on a plane. So we literally have people, researchers, sending a buoy to the other side of the world, and they work with local fishermen to deploy the buoy where they need it. Technically, Spotter is not different to any IoT Internet of Things device. It's a piece of hardware that's built to scale with onboard intelligence, so the data can be processed on board. It's a self-contained, autonomous turnkey system. So we have solar panels, rechargeable batteries, iridium communication. You don't really ever have to open it. You don't have to do anything to it. The data is sent to the cloud, and then we provide a dashboard online and an API, so you can fully automate the data streams to other data systems and models, for example. Connectivity is one of the reasons for the Spotter's attraction, and its ability to be part of something bigger, really. So it allows new crowds of users from regions and industries that would have never considered using wave buoys or marine data buoys in general otherwise. It's a completely new thing in the marine data world, and you don't need to be a scientist or engineer to collect the data, or you also don't need to pay another company, a contractor, to do it anymore. You can just do it yourself. And what's really exciting too is that we can now scale up the observation network. That means we can stop thinking about the unique instrument that doesn't have any redundancy, but instead we can think of a network of sensors, an array, as the instrument itself. And we can step away from the hardware and focus on the data and the insight it provides. But what's the future like? This is where smart mooring comes in. So the initial success of the spotter buoy was really quick and created a worldwide community of really passionate users. And a lot of them had some pretty crazy ideas about adding some more sensors to it. So since the beginning, people have been trying to add more sensors using duct tape or wire, with more or less success. So we realized that the Buoy was really producing more power than it needed, and it made us think about the next phase for our device. We decided, let's just do it ourselves. Let's work on that integration ourselves, do it right. And smart mooring really is an evolution of the spotter buoy. So in that case, the usual mooring that would be made of ropes and chains and shackles is replaced with a sturdy Kevlar cable with 2 wires running through it. So the surface buoy still operates as a wave buoy, but it can now power underwater sensors through the cable and allow their data to be accessible in real time. The connectors you see on this diagram can be placed anywhere in the water column or on the seabed. So you can really build any mooring you want. The idea is very much like Legos, if you will. Once you have the elements of a smart mooring, you can build anything you want. You can have a library, if you will, of different cable lengths, different connectors, and take this smart mooring to a different project, a different deployment depth with no problem. And with the smart mooring, you can extend the battery life of these underwater sensors. But more importantly, you can keep an eye on the quality of the data at all times, keep a backup on the cloud. Even the simple fact that you know that your sensor is fine is a big change. I'm sure a lot of people here on the call know that the traditional way to deploy underwater sensors is you put them in the water, walk away for a few months, cross your fingers the whole time, and hope that the sensor didn't tip over, didn't get buried, and that it recorded even at all. So no more anxiety around that now, because at all times you can get a hello world signal, just a sensor saying, I'm fine, it's all good. You don't need to send divers to check on me. You don't need to send a boat. I'm collecting data, but also you're always backing up the data on the cloud. So even if anything happens to the sensor, you will have backed up that data. You won't have lost anything. But more importantly now, because this data is available in real time, you can do a whole lot of really smart things in real time. So the data can inform real-time operations, whether it's for port transits, underkill clearance systems, for example, or coastal hazard warnings with storm surge monitoring, or for aquaculture management to show you if fresh water is coming in or the dissolved oxygen is dropping, this sort of things. But also from a weather modeling point of view, you can now do real-time assimilation of this sensor data into your numerical models. So we're already compatible with the RBR sensors. This allows us to offer a version of the smart mooring that includes a bottom-mounted Coda 3 pressure sensors. This means we can get real-time water level monitoring for storm surge, tide, infragravity wave studies, and have all this in real time too, obviously. So the USGS, for example, in US is now using this configuration to improve the skills of their total water level and coastal change forecast. And my colleague Zach here on the call is going to take it away from this point.
Hello, thank you very much, Seb. Somebody please let me know if my audio is not good. Yeah, I want to, as per usual, want to thank everybody who went before me. Seb, thanks for teeing me up there, and thanks to Eduardo and the RBR team. The partnership there has really been interesting because it's let us access different use cases and different utilities for our product that we didn't think were possible without such a partnership. And one of the really cool ones we want to tell you about is the USGS study here. Seb, if you wouldn't mind advancing the slide for me. Thank you. So we've partnered with the USGS here in the United States. They have been for a few years working on a tool to model and predict coastal resilience, and specifically around coastal erosion and flooding. I'm joining this call from Charleston, South Carolina. I'm actually in my childhood bedroom, which is now my mom's writing room. And we had 6 inches of rain from a tropical storm. I think it was Carlita that came and just dumped on us. And they closed all the streets. There were pictures of tourists, in thigh deep, knee deep water wading through downtown Charleston. And I'm also old enough, just barely old enough, to remember Hurricane Hugo. It came through right overhead here, and we lost everything. A lot of people did. And so this is a really cool project to me. It means a lot to me, but it also means a lot to everyone who's living on the coast, especially here as we're gearing up for what could be yet another really active storm hurricane season. And part of the tool that they're developing is to use LiDAR and other techniques to map the beaches, look at some of the bathymetry, some of the coastal areas, and how different storms and storm surges can contribute to flooding, and how erosion over a long time can change those profiles. It's an incredibly complex system. And the part of the project that we are able to join in on is the real-time monitoring and logging of this water level that Seb was mentioning. It's really made possible by the ability to get a lot of sensors out very quickly and adjust their location if needed, and kind of build this network that you couldn't do otherwise with very exquisite pieces of equipment. One of the meaningful results of this is not only will they be able to look at this data and adjust their models. And if you have a chance to check out the tool, I'm sure a lot of folks on the call are familiar, so I won't belabor the point, but if you have a chance to check out the tool, you can see it's very, very detailed, hyper localized, beach by beach, which is really essentially what's needed, because there's such a limited amount of resources, there's limited available knowledge of how the storm surges may react, that it really needs to be done beach by beach. And all of the data that's collected will go in to update those models and make them better, to give better predictive abilities for EMAs and emergency management personnel and decision makers to decide which beaches need renourishment, where you need to put a seawall. But the part that we're really excited about here at Sofar, because Seb mentioned this earlier, thank you for that, is that the ability to do something in real time can greatly increase the response time, or the speed at which we can. It's still some time away, but issue alerts, warnings, decide where to move resources, where to station the National Guard, so on and so forth. This is in really early stage of the project, but I really encourage everyone to check out what they've done already, and to keep an eye on this one, because I think this could really grow into something very meaningful. And for all of us living here at the coast, like my parents, it just means a lot to be able to decide when to go and when to stay, and know that these communities will be protected as much as possible in the future. There's another project I'd also like to tell you about, if you wouldn't mind advancing the slide there for me, Seb. This is also really interesting to me. I'm a diver. I'm a free diver and a scuba diver, and I've had every chance I can get, I'm out trying to be as much of a fish as I possibly can. And it's really the 11th hour for corals. Like I don't want to spend time preaching to the choir, because everyone on this webinar knows that. But one of the shocking things that we found while doing work with coral researchers and reef managers and dive tour operators is really, it's very difficult to get clear information, have a centralized repository, make decisions. Even university to university data sharing is complicated and oftentimes a little bit politicized, as people are fighting over just scarce resources. And we had a private investor come in and say that, hey, I want to change this. I want to build something, classic Silicon Valley style. Like, I'm just going to come in, guns blazing, pockets full of cash, right? But said, I want to build something. I want to do something new and different. I want to do something quick. And because of how we've configured the way that we approach hardware, and because we're still kind of developing, on a really short time scale, we jumped at the opportunity, and we were able to launch a new project right at the beginning of the pandemic. And we thought this was just going to grind to a halt. But Seb mentioned this earlier, but bears re-mentioning, we were able to ship these all over the world during a pandemic and have them remotely installed by volunteers, and continue to be what I would consider a very, very successful rollout of this project, despite all. I'll tell you a little bit about how the project is architected, and then a little bit about how the role that we play in it. Essentially, they're developing a web tool. This is a place where you can log in and get local data from your local reef, but it's also crowdsourceable. You can upload photos and videos, so sites that dive tour operators go to frequently are able to, take the same picture of the same coral head over and over and over. And Aqualink has provided a guideline for doing these surveys, these micro surveys. And the hope is that with a more standardized way of, very easy to do, but also standardized way of collecting visual data, in addition to the synthesis of publicly available, like the HICOM data and NOAA Coral Reef Watch data, that we can augment that with what's actually going on at the reef. And this is where we come in. What's been a real challenge with a lot of these reefs and planning which reefs need help or which reefs are going through a heating event, the satellite data is entirely insufficient. It can give you there's some good models in some locations, but other locations just nearby have wildly different effects. And that's obvious when you think, you dive down and it gets colder as you dive, or in some places it's very shallow and it doesn't. The ability to get a temperature sensor on the reef, measure live data both on the surface and at depth, kind of in the leaves and the branches of the coral, and be able to show how that correlates visually is hugely powerful. We think it's hugely powerful. Aqualink thinks it's hugely powerful. And I think this is the first year of the project. We're hoping to scale up this year. And one of the end goals here is, just like with the coastal resilience, there's a very small amount of resources for a very large problem. It's like, where do you focus your resources? How do you know when to activate your team to fly out to investigate something? And what we're hoping to do here is kind of consolidate those resources, both for, not just being witness to what's happening, as often the phrase is used, but also to find out what places are not affected and why. And potentially this tool can also be used for rebuilding reefs or growing reefs. Some of our earliest partners are part of the nurseries and coral resilience programs in Australia, Hawaii, and other places. So it's a really cool project. So if you want to click over to the next slide here. Yeah, thank you. So we've had such a huge response. Hundreds of sites have applied for this program. If you're in front of a computer right now and you can open up a new tab or something, you can aqualink.org and see the map. Everywhere where you see the blinking pentagon icon, that's where one of our units is installed and recording live data. And again, this was all done during the pandemic, so we're really proud of our ability to do that. And it's partly because it's so easy to get these things in the mail. They're under no air freight restrictions or anything like that. And so it goes through FedEx or DHL, something super easy. And then you can install it with the kayak, paddleboard, small boat. You don't need a big boat with an A-frame and a winch. One more slide, please. The web tool that they're developing is going to, like I mentioned, it's going to pull in data from a lot of different places. It's also accessible via, you can download it as a CSV or a JSON, but it really, the power, the ability to do this was given through our API, right? So beyond just reporting real-time data through our own dashboard, you can take that, and this is really a prime example of what you can do with the provided API, and it's evolving it. It's super modern. It's very responsive, and we're adding new stuff all the time. And so if you would love to talk to us about some of these projects that you want to try to do, it's a great opportunity, a great timing right now to chat with us. The other thing that's really interesting is we've been able to react. We've had some sites that are going through cyclones in Western Australia or heating events. And so over Iridium, we've been able to adjust the sensor parameters, maybe sample a little more frequently, or with the cyclones that came through, we were able to increase the wave data to full spectrum so that we were able to see what was really happening. And then the last thing that's kind of enabled this to make this really successful is we've been able to do processing both on the device and in the cloud, and being able to offer opportunities to add value at every level of this data, from the sensor all the way up to the device, all the way up to the cloud, has really enabled our customers to insert value where they see it. And whether that's something full stack like Aqualink, or something more detailed like up-to-date reports or push notifications or alerts, like all this is possible with the way we've architected our hardware stack. It's been really cool to see these. There's a lot more that we have coming down the pipes here, and a lot more projects like this. So if there's folks on the webinar in the Q&A session who'd like to ask specific questions about how all this works, like that's really what we're here for, and we're really here to talk to you. And I want to thank you guys for getting the opportunity to get up on a soapbox and talk about these two projects, which mean a lot to me and the rest of the team here at Sofar. Seb, did you have anything to add?
No, I think we've said everything. We'll probably work on the questions, if any, at the moment. I see the question, are divers required for smart moorings and spotter deployment in water depth of 150 meters or so, especially in these COVID circumstances where local fishers deploy the equipment with remote technical support from overseas? That's one for you, Zach.
Yeah, definitely. Divers are not required. So the data cable is also a strength member. So we've developed it to hold, I think it's 2 kilonewtons working load. So you'll be able to raise and lower weights with that. So if you're in deeper environments or areas where diving isn't safe, or we run into this a lot of universities are like not able to dive. They have to contract out, or because of COVID, they weren't able to. So we at Ocean Beach here, or there in California, we raise and lower this on a davit. Diving is a great way if you need more weight or you have some more complicated bottom attachments to do. It's a great way to do it, but it's definitely not required. That's a really good question.
And now there's a question from Shelby about whether we considered cellular transmission for the buoys. Answer is yes, very much so. It's fair to say we developed the initial version of the spotter buoy to be one version that would work everywhere on the planet. And so the common denominator was to use Iridium. That means the exact same buoy can be deployed in US, in Europe, in the Philippines. And that allows us to keep the cost down, really. But we also know that the ongoing Iridium costs are quite expensive. So we include the first year of data with our buoys, but after that, yeah, it's about $84 a month. We're working towards a new telemetry provider for over the air, like a satellite provider, that will reduce cost in the next few months, but also like 4G is very much on top of the list. And I'm doing a lot of internal lobbying to try and get this built as soon as possible, because it won't just reduce the cost, it will also like give us a much bigger data pipeline from the buoy. So we'll be able to get a lot more parameters or even the raw data from the buoys. So you can do a lot of processing off site, and we'll be able to get even more and more data out of the buoy, more granular spectral data, for example. So yes, we're working on this. I know I may have been saying this for a little while, but we're committed to doing this. And this question from Kevin, is the wave data directional or non-directional, and does the spotter record wave spectra, and was it validated against established platform? Yes, yes, and yes. So it's a directional wave buoy. It's measuring its motion in the 3 axes using GPS displacement. So everything is done directionally on board, and you can decide to receive either just the standard wave statistics, so significant wave, high period, direction, or the full 2D spectrum from the buoy. And there's a few examples online where you can actually see folks using that spectrum being delivered over the air, and they use a little spectral plot to put it on their website. So the folks at the Wild Waves in Western Australia, for example, have a fleet of buoys on the west coast of Australia, and they actually show some polar plots, are quite neat. And yeah, so that's completely doable. And all the buoys we have also deployed in the open ocean as drifters, so that's kind of a separate project, are also reporting wave spectrum in real time. In terms of validation, yes, the buoy was validated initially next to an Axis buoy in California, and since then we've had a lot of instances of comparisons right next to other sensors. So there's a plethora of those. There is a paper out there that I can share afterwards if you want, that shows the initial validation and how we came up with the processing algorithm and everything. And since then, there's been a lot of validations done either by us or some of our users. Jose is asking about how we get wind data. So the wind data is a proxy measurement. It's not a direct measurement, it's calculation. So essentially what happened is one day we had a spotter buoy deployed right next to a full metocean buoy that has an anemometer. And so we're measuring full spectrum, and we realized, well, let's see if we can look at the high frequency part of the wave spectrum and derive the wind. It was kind of just a scientific question, really. And our lead scientist, Peter Smith, started working on this. And it's essentially just retro engineering the fetch, the wind, and the wave creation. And it turned out it worked really well. So we tried it a few other sites and we realized it worked really well. So we implemented it into the firmware of the Buoy. So it comes with some caveats in that this calculation really only works in open ocean, but in areas where the fetch is not limited. So that means like in bays, harbors, or right next to cliffs and everything, the local top, if you will, the high frequency waves are not a true reflection of the wind. So you need to be kind of in the open ocean to have this really work. But also like it's kind of icing on the cake. It's a nice data to have. It gives you a good sense of the sea state and also the wind changes. But if you're using wind data for critical operations or design criteria, please don't use that. Just use a proper anemometer. Roxanne is asking the question about at what point does adding sensors along the cable interfere with the accuracy of the wave measurements from the buoy at the surface, and how much is too much?
I think I
Want to
might
take this one, Zach?
Yeah, I think I may be able to feel this. Do you mind rolling back to slide number 5 with the diagram?
With this one?
Yes. Yeah, excellent. First, I maybe we'll do this offline, but I'd really love to know what you're thinking. I love the idea of what point I imagine more sensors or larger sensors. That's really interesting to me. So I'd love to hear what you have in mind. But if the question is about payload and weight and how that could affect the GPS displacement, generally speaking, if you have the anchor properly sized and the float properly spec'd out, most of the weight of your sensors or the negative buoyancy or drag caused by the environment is taken up in that area. And this catenary loop between the surface float there, it's rotating, but that surface float there at Bravo and the spotter there at Alpha, that catenary loop allows the spotter to move freely. And so there really is no physical limit what you would be able to attach subsurface.
So how much is too much is right now, there's not really any limitations. Really, the only limitation we have at this stage is the available power. So some sensors are more power hungry than others, but the weight really is not really a limitation because we can always overcome that with subsea float, sorry. And as Zach mentioned, that top float, which we always recommend using with our buoy, is taking all of the tension, all of the weight. Question from Sean, can you provide some comments on general maintenance calibration requirements for long-term deployments? So first, calibration for the spotter buoys, no calibration. There's no moving parts because it's a GPS-based buoy and that sensor doesn't drift over time. There's no accelerometer or gyro compass to recalibrate. You never have to take your buoy, put it in a box, send it back to wherever at cost to get it recalibrated. So that's pretty handy. You don't have to worry about that. Also, it's got solar panels and rechargeable batteries, and you don't have to swap those either. The only maintenance that's required is around biofouling, because as far as I know, there's nowhere on the planet where you can deploy a buoy and there's not crazy animals and algae growing on it in no time. So we recommend a visual inspection at the very least every 6 weeks. And typically you take like a scrubber with you and just wipe everything before it really gets too intense. You wipe the solar panels and so on, and that's about it. And that can be done with the buoy still attached to its mooring because it's quite lightweight. You can really just kayak to it, put it on deck, scrub, and that's it. So that's the only maintenance required, because what would happen over time, your spotter turns into a Franken buoy and there's mussels and barnacles growing on it and it becomes a huge sea monster, and it can really affect the weights following the waves. And over time, really, it could get partially submerged. And that's about it, really. I don't think we have any more questions, Eduardo. Do you have anything to add?
Well, maybe just before we go into those two, just to add to the biofouling and the calibration schedule, in terms of the sensors that we're integrating, just, if that answers part of the question, Sean, is for the Coda series, that will be, we expect that they remain within spec for a year. So we generally recommend an annual calibration of the sensors themselves. And that's beyond any kind of wiping of biofouling, as Sebastian mentioned. So that would be good to take into account as well if you have any of our instruments. Of course, some of the instruments, depending, you know, how we increase the number of sensors and type of integration, may require more frequent maintenance, not only on biofouling, but also if there is any you know, high power load sensors that may have their own battery, that those have to be replaced in time. Even if we're sending the stream through the smart mooring, there may be batteries in the loggers that need to be replaced. So just another consideration.
I'll move on with the questions because there's a few that came up, if you don't mind. So Giles was asking, the buoy is quite small. Do you have any instances of theft or vessel hits? Yes, the buoy is quite small. You can actually see I have a wave buoy in my office on my right shoulder. This is the true size. Also acts as my paperweight. So theft, and I see another question about vandalism, which is very much a lot of this. It's the same thing. That's a big problem for every marine data buoy around the world. So I'm part of the data buoy cooperation panel with the WMO, and it looks like every nation on the planet that has instruments in the water has the same issue. We're lucky enough that the buoy is actually quite small, which means it's not quite as visible, doesn't look nearly as expensive and valuable as others. And there's nowhere where you can really attach a boat either. So they can't use it as a mooring and go fishing, for example, which is quite a good thing. Vessel hits, there has been a couple, but typically we recommend people do place a notice to mariners and also install the buoy out of navigation channels to start with. You kind of have to be a little bit considerate around here. But the best thing to do is always to work with the local community. We've had buoys deployed all around the Pacific Islands, for example, and there was a big campaign by the WMO who created a cartoon about ocean buoy awareness, and it's really neat. You can find it on YouTube. And it's basically targeting the coastal communities in the islands or anywhere on the planet, really, to just leave the buoy alone. It's here to serve you. It's going to be helpful to you know, capture the cyclones and coastal hazards and everything. And you really want to talk with the coastal communities and empower them so they can understand the value proposition of these buoys, and they can actually become caretakers of them, you know. And that's an approach that's working really well all around the world. You know, they really get involved in the project, and so whether it's the local fishermen or it's a local tribe, it doesn't matter. You find a local group that can foster collaboration with all the local marine stakeholders, and it works really well. The other thing too is that because the buoy is GPS based, we always know where it is. As long as it's outside, we know where it is. And from your dashboard, you can set up a geofence, which is a virtual fence around the buoy. And if it gets out of there, you get notified right away, and you can switch to a rapid refresh of position, if you will. So you can see where that buoy is going if someone's taking it. And we've had researchers, for example, in Australia, that got notified that their buoy that was deployed in Vanuatu had moved, and she called the local police, and they managed to intercept the people that had borrowed the buoy in 30 minutes. And there's an article on our website, and it's really neat. You can see the track of the buoy and where they got intercepted, and then the buoy was instantly redeployed, and that was done all within an hour, I think. How long that powered cable section is currently, and do we make different length to get yes, and what is the cost associated with that? Okay, so there was another question about the 300-meter limitation too. Zach, do you want to take that on?
Yeah. So 300 meters is our theoretical limitation on guaranteed transmission of data on that cable on our communication protocol. That is no means like a hard stop. So if you've got things in mind, definitely talk to us, because we have some ways we could probably extend that. Practically, for most applications, it depends on a little bit of your power availability. So if you have only one sensor and you only need to sample once an hour, for example, it's much lighter of a task versus a ton of sensors all the way down, every 5 meters for 300 meters might be a little challenging for the current design. But again, I say it that way on purpose. The current design is very flexible, and we try to move quickly and adapt to these situations. So if there's other things you have in mind or you want to go deeper, it certainly is possible, with a little added caveat that we'll have to talk about how to do that feasibly. The smart mooring comes with these little nodes. These are breakaways that sit in between cables. Every node could have a sensor, but it could also just be like an extension cord, cable to cable. Cables come in 5, 10, 25, 50, and 100 meter lengths. So you can kind of like pick and play, or plug and play, pick which cables you want. We don't recommend going much over 300, although you might want to chat with us about your use case, because we might be able to figure out ways to do that. And the hard limitations there are just power availability. As you get longer, a lot of that power is taken up by internal resistance to the cable. And then also from our communication protocol, not being able to guarantee strong communication, although we think we can get longer with that, doing a couple of things. So thanks for the question. If I didn't answer that completely, or you'd like some more detail, please just post in the chat window there.
I'll take Shelby's question about the GTS. So for folks that don't know it, the GTS, the global telecommunication system, where people can opt to share their ocean data, and so it becomes it becomes available to the general research and weather community. We do not currently push our data to the GTS. The data that's collected by everyone's buoy is yours. So it's yours to do what you want with it. So we provide an API, which means you can quite easily do local backup in your own servers. And if you decide to push the data to the GTS, that's really up to you. Well, we're working more and more with national weather agencies and national or large observation networks, which means that a lot of those people are now really interested in automatically sharing this data to the GTS. So that's something we're looking into, have a function on the dashboard or else to a toggle to say share to the GTS. But as you know, there's a very high standard that comes with the GTS. So the metadata has to be extremely well documented. The data format has to be impeccable. So it's not a trivial exercise. And we want to make sure that if and when we do that, we do it right, so we don't contaminate the great data set that the GTS already has. Okay, so Kevin is saying that he was mostly interested in current profiling. Tired of acoustic modems failing? Yes, aren't we all? So current is a bit of a tricky one, because that's one of the recurring questions is, can I put an ADCP to my smart mooring? Right now, today, not really, because traditionally, quite frankly, the ADCP's current meters have been pretty expensive and power and data hungry. And we try and keep our sensors, our system really low cost. So it kind of felt like, I always make that metaphor, it felt like putting an ADCP to a smart mooring is like putting Formula One tires to a Honda Civic. It was just, the prices really didn't match. It's a bit silly. There's new generations of ADCPs coming up that are way more modular, much smaller, and more affordable too. So we're looking into it. We're talking with manufacturers, and we're currently working on a project that's also going to make it much easier to plug anything you want to our smart mooring. So it's going to be a kind of a universal plug, if you will, where people with ADCPs or else, and whatever sensor you own, you'll be able to just build the integration yourself.
I was going to say something regarding Kevin's question as well. It kind of drifts a little bit away from what the smart mooring is doing, but you can reach directly to us if you want, and we can maybe help a little. We generally provide the mooring line modem with some systems that already have RBR instrumentation in it, but we do integrate some ADCPs, and again, you do need a jacketed mooring line, but we have, in that case, a limit of 4,000 meters. So, you know, it may be applicable depending on how broad and what other instruments could come in. But maybe if you want to send a note, I can provide my email as a direct message to you. All right.
And just to bounce back on what on Kevin's question. So since we started this smart mooring project, obviously it's caught the attention of a lot of researchers, scientists, ocean observers around the world, and we're always working on the next version. We're always building new integrations. I wanted the integration with RBR to be the very first one we did, and we're lucky that the RBR folks were really keen to start working with us from the get-go. So that was the first integration we worked on. I really wanted that bottom-mounted pressure sensor, and we got it, so I was quite happy with that. And so we have folks contacting us with all kinds of ideas about this, what to install on a smart mooring, and we just have to focus. At the moment, we can do anything basically. We just need to do it at scale, because we're trying to keep the cost down. As I said, we want this total system to still be affordable. So if you just do one thing, a custom job, it's never cheap. So we're not really interested in doing that. But if you have a project that's looking at putting quite a few monitoring stations with a bespoke type of sensor package, whether it's ADCPs or Ls, just contact us and we can sort it out. All right, no more questions. Also, it's 5 past the hour, so I think a lot of people may be moving on.
Yeah, I think we've done well.
Yeah.
So thanks. I mean, I don't want to take on the goodbye part, so we can do it together, but not in unison because it'll sound weird. Thank you, Zach and Sebastian and Ashwin and everyone else that helped. Thank you, Krista, for helping us organize this. And again, everyone, if you have any questions, you know, you can reach us through our websites or through the emails that we provided. The recording and the slides will be made available. And yeah, it's been great, and we really look forward to this partnership between RBR and Sofar, and you know, keep an eye out for all the new developments over the next few months.
Thank you, everyone. Have a good rest of your day.
Thank you.
Bye.
Take care.
Bye-bye.
Bye.